The goal of this video is to review key parts, key characteristics of different kinds of graphs, what makes them unique, what sorts of things are important to know about them so that we can build on that knowledge in the future. So just some reminders about functions and different properties of their graphs. A little review on domain and range first. So domain is talking about the x values. When you're looking at a function and you're thinking about domain, things you want to keep in mind are vertical asymptotes. If you're looking at a rational function, make sure that you're thinking about what is allowed to be plugged into this type of function. Is there a value that's not allowed to be plugged in? And then when you're writing domain in interval notation, you're really going to be thinking left to right and asking yourself what x values can be used. So here are those ideas. Now let's talk about range. The range of a function is talking about its y values, so you need to also consider horizontal asymptotes when we're thinking about rational functions. And we're going to be thinking not left and right anymore, but down to up. What is the lowest the y value can go? What is the highest the y value can go? So we're thinking about outputs of the function. So here we have that information. Now interval notation, I'm out of space up here, so I'm going to come down here. Interval notation uses parentheses and square brackets to write the domain or range in a way that you can understand what interval it's talking about. We have seen this in some of the previous videos already, but I want to make sure that you know how to write something in interval notation. So when you are writing something in interval notation, you're using parentheses if something is not included, such as plus or minus infinity are never actually included since you never get there, or if there was an open circle, or if for whatever reason the value was approaching an asymptote, something along those lines, you would use parentheses. You use square brackets when that value is included. For example, the vertex of a parabola, that value is the lowest value or the highest value, so that number would be included. You can have a combination of these, so you could have an interval notation that had square brackets on one side and parentheses on the other side. And then remember that when you are writing this out, you are writing the smallest number, or the smallest something can ever go, which could be down to infinity, or down to negative infinity, I should say, comma, the largest value. So, for example, if I had a quadratic function here, and let's say that this vertex is the point 2, 3, my domain, in this case, it is going left forever, so my domain would go from negative infinity, which is not included, and to the right forever, up to positive infinity. That would be my domain, all real numbers, which makes sense. You're allowed to plug in any x value into a quadratic function. Now the range of something like this, we're talking up and down now. Well, the lowest that this ever goes is this point right here, and the y value, which is what range is, the y value of that is 3. Then it's going up forever, so that would be the interval from 3 to infinity. So if you need more help on that, check out another video on domain and range, but I just wanted to review domain, range, and interval notation as a whole. The next thing we're going to talk about is even versus odd functions and end behavior of functions. So some functions are even, some functions are odd, and some functions are actually neither. So it is possible that a function could be neither. It doesn't have to be even or odd. So what does it mean if a function is odd? Well, an odd function has symmetry about the origin, which means if we folded the graph along the line y equals x, everything would line up. Or you could rotate it 180 degrees about the origin and everything would line up. It means that if you had a point x, y, you would also have the point that is the opposite of both x and y. So how do you test for this? You check to see if f of negative x is the same as negative f of x. Meaning, if you replaced all of the x's in the function with negative x, would you get the opposite of the entire function? Now that's odd. So a commonly thought of odd function would be f of x equals x to the third. Because if I substituted in negative x, I would have the opposite of the entire function. Now, even functions always make me think of quadratics. Not every quadratic categorizes or follows the rules of an even function. So an even function is a function that is symmetric about the y-axis, which means that if we folded the function along the y-axis, everything would line up. So if we had the point xy, we would also have the point negative xy, meaning that you could plug in negative x into your function and the output would be exactly the same. A great example of this would be y equals x squared. If I plug in negative 2, I get 4. If I plug in positive 2, I get 4. So symmetric as in I could fold it over the y-axis. So not every quadratic function is symmetric about the y-axis, but some of them are, and those would be even functions. So remember that it is possible that a function is neither odd nor even, but this is how you can test to see if a function is odd or even. There's also another kind of symmetry that doesn't fall into odd or even, and that's x-axis symmetry, which means that if we folded the graph along the x-axis, everything would line up. So for each of our x values, there are 2 y values that would occur. So x-axis symmetry would not yield a function, right? It wouldn't pass the vertical line test, but it's still a type of symmetry that could help us understand more about what's going on with a function. And then the last thing we're going to talk about before we get into some examples is end behavior of a function. So end behavior is talking about what is happening to the function as x goes to positive and negative infinity. And I'll show you one way to write that out and how to look at that in these next examples. So thinking about domain and range and how to represent that in interval notation, paying attention to x-axis, y-axis, or origin symmetry when it exists and how that might make a function even versus odd. But let's actually look at some functions here and try to determine important information that we can determine about those functions. So here we have 3 functions. So let's start with A. So the directions say, given the function, determine if it's odd, even, or neither, and describe the end behavior. So what I notice on A is that I have a 4th degree polynomial, which means the graph is going to look something like this, sort of like a W-shaped graph. Just knowing that is incredibly helpful. Now that doesn't mean necessarily that it's even, which is my gut is telling me, but what it does mean is that I could talk about the end behavior. So I'm actually going to talk about the end behavior first. The end behavior of this function, which since there is no negative in front of this x to the 4th, I know that it is going to look something like this and open upward. So what I'm asking myself is, as x approaches negative infinity, so as my x's get smaller, what's happening to the function or the y values or the outputs, f of x is approaching infinity, or you could put positive infinity. What's happening as x approaches positive infinity? So on the right, as my x's are getting bigger, the function is still getting bigger. You could also write this, since it is the same as x approaches plus or minus infinity, f of x approaches infinity. Since it's the same, you could write it as one statement. If there was different behavior happening on the left and the right of the graph, you obviously couldn't write it as one combined statement. Okay, let's check for even versus odd now. So how do we check that? What we're saying is that x is becoming negative x. So f of negative x would be negative x to the 4th minus 2 times negative x squared. Now, if I have negative x to the 4th power, it doesn't really matter what's happening on the inside. Something to the 4th power is going to be positive. Minus 2 times negative x squared, again, is going to be positive. So what I need to do is I need to compare this with my original function. And I need to ask myself, are they exactly the same? That would make it even. Are they exactly opposite? That would make it odd. Or is it a combination? That would make it neither. So exactly the same, even, exactly opposite, odd. Otherwise, it's neither. So these two things are exactly the same, which means f of x is even. It is an even function, which helps us analyze its behavior and its symmetry. Go ahead and pause the video. And on B, plug in negative x and simplify as much as you can. So here I've plugged in negative x. Negative x to the third power is going to be negative x to the third. Negative 2 times negative x is going to be plus 2x and plus 1. So let's look at the signs, comparing this to this. Are they exactly the same? Definitely not. It was positive x to the third, now it's negative x to the third. So they're not the same, so it's not even. Are they exactly opposite? Well, x to the third is, 2x is, but the problem here is this constant isn't changing signs. This constant isn't changing signs, so this is going to be neither. So yes, you did guess it. If a function has a constant, it's never going to be an odd function. All right, go ahead and pause the video and work through C on your own and then unpause the video to see how you did. Here we go. Negative x to the fifth is going to be negative x to the fifth, so that's going to keep its sign. Minus negative x is going to become plus x. So here's my h of negative x, here's my h of x. Are they exactly the same? No. Are they exactly opposite? Yes, both terms changed sign, so this is an odd function. What we didn't do yet on B and C is talk about end behavior, so I'm going to go ahead and do that now. So thinking about this, this is a degree 3 function, which typically takes the form like this since it is positive. Since the leading coefficient is positive 1, it should look something like this. So as x approaches negative infinity, as my x's are going further to the left, the graph is going down. F of x approaches negative infinity. As x approaches positive infinity, as my x's are going more to the right, my function is going to positive infinity. So this is describing my end behavior on B. Go ahead and pause the video and see if you can do end behavior on C all on your own. All right, a 5th degree positive is going to look similar to a 3rd degree. There's probably some more bumps happening there, but again, we care about the end behavior here. So what's happening on the ends is actually going to be exactly the same as part B. As we go more to the left, or as x goes to negative infinity, so does f of x. And as x goes more to the right, goes to positive infinity, so does f of x. So hopefully from this, you're getting the idea of determining if a function is even or odd, or neither, and how to identify the end behavior. And again, what we're really focusing on is being able to look at a function, kind of have an idea of what the shape would look like and how that helps us understand more about the function. What we're going to do now is go back to the basics and recap the basic parent functions. And I would say we have a couple in here that are a little less basic, but still worth reviewing. The basic parent function. So what I want you to do really quickly is pause this video and go ahead and see if you can come up with the type or the name of that type of function for any of these 6 functions here. All right, number 1 is a degree 1 function, which makes it linear. Number 2 is quadratic. If now you understand what I'm asking, you can pause the video and see if you can identify any of the remaining ones. Number 3 is cubic. Number 4 is square root. Number 5 is an exponential function, but this is specifically base 2, since the base of the exponential is 2. This is one that's not as specific, right? In order to have an exponential function, we have to be able to identify the base to graph it. And then number 6 is a rational function, if we just want to call it the most generic name that we can. So let's go ahead and graph now. Number 1 is a line. The y-intercept is 0 since there's no plus b. The slope is 1. The most basic version of a line basically goes diagonally across the grid. And you should use a straight edge to connect that. Now here's our line. Let's think domain and range. And I'm going to write them over here. I don't think I have enough space down there. The domain, the furthest left this ever goes, well, it goes left forever. So it goes left to negative infinity. It goes right forever. So it goes right to negative infinity. The range, it goes down forever, so negative infinity. It goes up forever, so positive infinity. A linear function has domain and range, negative infinity to infinity, or all real numbers. All right, number 2, quadratic function. The vertex is going to be at 0, 0. A quadratic function has, or the base, the The parent function for a quadratic function is symmetric about the y-axis. So we can just plot the basic points and connect. And hopefully yours looks a little more rounded here than mine does. So the domain is still going to be negative infinity to infinity. It goes left forever and right forever. The range, though, it doesn't go up and down forever. It goes up forever, so it goes up to positive infinity. It goes down until it gets to the vertex, which is 0 and included. Okay, number 3, the cubic function passes through 0, 0, 1, 1, and negative 1, negative 1. This makes it look linear, which it most definitely is not. But if I plugged in positive and negative 2, I would get 8, which doesn't fit on my graph, but I'm going to just kind of give you an idea of what that would look like. This should be a little bit more angled here, hard to do on an iPad. So there we have it. In this case, the domain, what are we allowed to plug in? Can we plug in negative numbers? Yes, all of them. Can we plug in 0? Yes. Can we plug in positive numbers? So the domain is all real numbers. And that's really what I'm thinking through. What am I allowed to plug in? Whatever I want. Looking at the graph, are there negative numbers? Yes, it's going down forever and it's going up forever. So all real numbers is the domain and the range for the cubic function. Square root function. So I can't plug in negative numbers here, so my sort of vertex, you can think of it as, would be 0, 0. If I plug in 0, I get 0. If I plug in 1, I get 1. If I plug in, what's the next number I can take the square root of? 4. Well, I could take the square root of all the numbers, but the next one that gives me an integer would be 4 because the square root of 4 is 2. Now here, the domain and range are going to be different. When I'm talking domain, I'm talking about what am I allowed to plug in. Well, I'm not allowed to plug in negative numbers if I'm talking about a real function, because I can't, in the real number system, take the square root of a negative number. So the smallest thing I'm allowed to plug in is 0. However, after that, I can go up forever. There is an arrow here going forever to the right. Similarly, with the range, what is the lowest this graph ever goes? It goes 0, and then it goes up forever. 2 to the x, you can really think about this as in making a table. So 2 to the power of 0 is 1, 2 to the first power is 2, 2 squared is 4. And then what's happening on the left-hand side? 2 to the negative first power is 1/2. 2 to the negative second power is 1/4. So with this graph, there is a horizontal asymptote at the line y equals 0. And when I connect this graph, it looks like this. And it is not crossing that asymptote. I should have a better arrow here. There we go. So, asking ourselves about the domain, it goes forever left and forever right. There's no x value that I am not allowed to plug in. I can plug in anything I want. The range, though, it is going forever up, so the right-hand side will be positive infinity, but it's not going down forever. It looks like it's going down and getting closer and closer to 0. But it will never get to 0 because of that horizontal asymptote. So I need to have parentheses instead of square brackets. All right, number 6 has some asymptotes happening here. X is not allowed to be 0. X is not allowed to be 0 because then I'd have 1 over 0, which is not a thing. That makes sense. There's also another asymptote, a horizontal one that's happening at y equals 0, because what would make this 0 is if the numerator is 0, and the numerator can't possibly be 0. Since it is a constant, the numerator is always going to be 1. Now you could make a little mini table to come up with some values for this, but really, if x is 1, then the function is 1. 1 over 1 is 1. If x is 2, then I have 1/2. So this is going to make sort of a exponential looking if you look at just one side. And similarly here, it's going to approach both of those asymptotes on the left and the right. So how do we write the domain and range for this sort of very weird looking function? Well, the domain is basically everything except for 0. We're allowed to plug in all of the numbers except for 0. How do we write that in interval notation? Let's come down here actually. The domain is negative infinity to 0, and then 0 to infinity. So basically everything not including 0. Your range is going to be exactly the same. Negative infinity to 0, and then this little u in between means the union of those two intervals or those two intervals together. So now that we've graphed our parent functions, we've talked about their names, their domains, their ranges, what they look like, we're going to look at some functions, some rational functions, some different types of functions, and we're going to talk about their domain and range without graphing them. So here we go. So I want to remind you to consider some things. Consider if there's an asymptote, what that might be. Consider if there's a value that x can't be or if there's a discontinuity. And consider what is allowed. What are you allowed to plug in as your x values? So let's talk about domain on number 7. The first thing that I notice is that I can't have -1 in the denominator. If I had -1 in the denominator, I would have a fraction over 0. So there is, I'm just going to make a little note, there is a vertical asymptote at x equals -1. That's the only x value that's not going to work here. I could plug in -1.1, I could plug in 1,000, I could plug in -1,000,000. Everything else will work. So my domain is going to be -infinity to -1 union -1 to infinity. My range, now when I'm looking at range, I want to look at horizontal asymptotes, and it's probably been a while since you thought about this, but in a previous course you should have learned to look at the degree of the x values, and that is they both have a degree 1, so I'm going to divide those leading coefficients. So there is a horizontal asymptote at x equals +1, which means my range, and you can graph this on Desmos to double check me, is going to be everything except for +1. And that makes sense. Look at number 7 and then go back and look at our graph for number 6. This type of function has 2 asymptotes. Okay, number 8. Let's draw a little line here. Number 8. First thing I'm asking myself, x values, and I'm going to just factor the denominator. That's going to be x minus 3, x plus 2, which means x is not allowed to be 3 or -2. There would be asymptotes at both of those values because they would make the denominator of the fraction equal 0. What else do I notice about x values here? Well, based on this numerator, I'm not allowed to plug in anything negative, so this value kind of doesn't matter because I already can't plug in a negative number. So the lowest my x can ever go for my domain is 0. It goes up to 3, but it doesn't include 3 because if I plugged in 3, the denominator would be 0. And then it goes from 3 up to infinity. The range now could really be anything. The top of the fraction is always going to be a positive number since I'm square rooting a positive number. So the output, the numerator output is always positive, but the denominator could be positive or negative. The only other value I want to question for myself is it possible that this function could be 0? Well, what happens if I plug in 0? The numerator is 0. So yes, it is possible that the output could be 0, which means the range of this function is going to be all real numbers. I could have negative values come out. I could have positive values come out. So it's going to be the interval from -infinity to +infinity. All right, I encourage you to pause the video and see if you can find the domain and range for number 9, and then unpause the video and see how you did. So hopefully you've had some time. In order for me to take the square root of a number, I need to take the square root of something that is greater than 0, which means that this gives me that x has to be 4 or more. Could it be 4? Yes, because that would just mean that I'm taking the square root of 0, which is allowed. But it couldn't be 3, it couldn't be 2, because then I'd be taking the square root of a negative number. So my domain is going to be from 4 to 0. If this is my domain, if I plug in 4, what is my output? My output is 0, and this will also go up forever. So let's recap what we have learned in this video. We talked about and spent a lot of time focusing on how to write domain and range, how to identify domain and range from a graph, how to identify domain and range from a function. We spent some time talking about the behavior of a function, the end behavior, looking at what's happening as x goes to positive infinity and as x goes to negative infinity. We spent some time identifying if functions are even, odd, or neither, and what those different kinds of symmetries can mean when we're analyzing a function. So the goal here is that I could throw a function in front of you, and you could tell me as much as you can about that function. What does it look like graphically? What's its basic shape? How could we talk about domain and range? Does it have symmetry? Because all those things are really going to build and solidify the understanding that we have for the calculus to come in the future. So post any questions below or write them down. I look forward to supporting you on this. Thanks for listening.